I will show some industry examples that MODSIM can really help finding the best design alternatives. The simulations in this presentation was made by my colleagues in Canada, Optimix. I want to thank them. Again, my name is Björn Lundin. I'm the technical manager of TECHNIA Simulation. And TECHNIA Simulation, what we are doing, we are helping our customers finding the best software solution. We are supporting them, we are training them, and we can also help out with engineering services. So today we are above 80 experts, and we are covering 16 countries, mainly in Northern Europe and North America. So today I will show you 4 use cases where we have used MODSIM. So one use case is a suspension link arm in the automotive industry. Then we have the design of a rear impact guard, which is used under trucks and trailers, so you don't to prevent underrides. It's also from automotive industry. Then we have a thermal analysis of a cardboard box design from the consumer packaged goods industry. And then we have a cooling or battery energy storage system, which is an energy industry example. So the first one is this suspension link. It was made by casting steel. The OEM, they wanted a lighter and cheaper design, but it should still fulfill the physical properties, so it should have the correct stiffness. So one idea was to use forged aluminium instead. So we decided to give it a try. Of course, the bushing positions, they are fixed. They cannot be changed because it's already in a suspension system, but everything else can be changed. So we have a parametric model with the outer diameter of the bushing, the rib, the body, the number of pockets, the fillet were parameters that we optimize. And we have an initial value that we start from. It's the original design. Then we have the design space, so we have minimum and maximum values. So we try everything in between the minimum and the maximum values. And there is also a step size. So we don't check everything, but we have an increment when we test this. The objectives, of course, mass, we want to minimize. Then we must make sure that we are under the stress or the yield limit. So we check the stresses. And then we want to maximize the stiffness, so the reaction force and the buckling, eigenvalue buckling. And the load cases, we have 3 linear load cases that come from the OEM. So it's more or less forces and moments that are applied on the bushing. Then we have the compression load case, which is to try out eigenvalue buckling. And the third one is linear and nonlinear tension. So just pulling it and check the limit for tension. So we run 100 design alternatives. So to the left you can see the plot. It shows in this case mass versus reaction force. We have a limit on 550 grams because that was the weight of the old one. We don't want to be above that. And then the reaction force shows gives an indication of the stiffness. In the middle you see the IC view of the design being tested. And then to the left you have the input and the output. So you can see as we change the design variables, we also get new outputs, so new results. This is where we ended up, this design. So as you can see, this is the initial design, this is the new design, steel, aluminium. The new one, it matches the physical properties exactly. So it has the same stiffness, same eigenvalue buckling modes, but it's 41% lighter than the old one. So it's It's lighter, it's cheaper, and it also matches the old physical properties. Of course, we found also other design alternatives. So one here that is really light, it's 48% lighter, but the stiffness are not matching exactly. It could be used, but we want to keep the same load path as the original one. Same here, one which is also lighter but 4 times stiffer. So maybe not the correct one to use. The second design alternative is the rear impact guard. As I said, it's mounted under trucks and trailers to prevent underrides. It must fulfill some special standards. So we have a standard from North America that must be fulfilled if you should sell or use this. It says that the max deflection when you test this should be less than 125 millimeters. And the test is pushing here by 100 kilonewton. At the same time, the minimum energy absorption should be above 5,650 joules. So this is a quite challenging optimization, because you want something to be stiff so it doesn't deflect, but at the same time it must absorb a lot of energy. So quite challenging. This was the original idea, a box, a square with some imperfection. Of course, we want to minimize the mass. We want to maximize the reaction force, but it should not be too high, not too low. So we aim for 100 Newton, kilonewton, and then the absorption energy should be maximized. So this is the result from, Here we are trying out 180 design alternatives. As you can see here, we are aiming for 100 kilonewtons, so it's a quite narrow window. It must also, we have the absorption energy on the y-axis, and it must also be above 5,650. So we have a quite narrow window here. With this design, you can see that it actually fulfills the requirements, but it has a really high peak in the beginning, meaning that it's not stable. It's unstable after the initial reaction force. So we wanted another design. So we tried out first the diamond grid design, which would probably work, but it's also very difficult to manufacture. So instead, we decided to try something more simple. It's two circles. So you just bend a steel plate. And with this design, we needed to include also the full frame, because to get realistic boundary conditions, it becomes so stiff, so we need to include more to get realistic boundary conditions. And as you can see here, we have a lot of design alternatives matching what we are looking for. So this design looks better. And here is the final result. So as you can see, at 100 kilonewtons, we have deflection, which is 104 millimeters. It's below 125 millimeters. And we absorb 8,550 joules, which is also above the requirements. So we passed the standards. Third case is this cardboard box with some isolation panel inside to keep the food cold when it's delivered to your home door. The problem was here, the customer who produces this isolation panel, they wanted to make a change to increase the thermal resistivity. So they wanted to increase the cell size, because since the conduction equation is linear, when they increase the size, they also suspected that they would have an increased thermal resistivity. But the lab test showed something else. So they came to us and asked what to do. We did a simulation, and it showed up that when you increase the size, you also get circulation inside the cells, which causes convection. And convection is a heat transfer mechanism. So, yeah, not improved thermal properties. So, can we now find the best possible design then to be used in these panels? So we tested a lot of different design alternatives, so different designs. First of all, you can do some data analytics to learn how your design behaves. So in this case, we have cell size, thickness, skew factor, and here is the output, radiation, convection, conduction. And we can learn, for example, with increasing cell size, conduction is decreasing, which is proving what we said before. We also have correlation maps to see what the sensitivities are. So for example, cell size affects conduction. On the other hand, glue length has no impact at all. So maybe you can also reduce some manufacturing tolerances by reducing the glue length. From all the results, we can also do interpolation maps, so meaning that you can input any variables and you can get output, which in this case is thermal properties. So with any input, you get material data for thermal, meaning that now we can reduce or we can replace the more complex FEA model with just solid material and still solve the problem. So in this case, you see the velocity vectors on the left and the thermal simulation to the right. And here is the ice boxes, the food trays, and then the cardboard box. The fourth case is a power battery energy storage systems. This is used in places where you don't have access to electric power. So it could be some disaster places. Of course, when it's in use, it produces a lot of heat. It's filled with batteries. So we have 200 batteries placed inside this container. On one side, we have the HVAC. And then we need to design how the duct should look like, because we need to have a sufficient cooling and also even cooling. All the batteries needs to be evenly cooled. So how should this duct then be designed? We are looking at two variables, output variable. It's the total volume flow, which is dependent on the pressure loss. And then we have something called global homogeneity, which is the difference between the most cooled battery and the less cooled battery pack. And we want to decrease that, meaning if that becomes small, we have an even distribution of the cold air. This is the initial design, how it looked from the beginning. You see there are 6 holes, exit holes for the cold air, and it's kind of a straight design. So the question is, how should it look like? How should it be designed to get the best possible cooling? So we did a lot of designs. We tested a lot of designs. And this is how it ended up. Maybe not too obvious. You see the holes, they don't have like same size, the height and the width. It's also bent, so there is some angles that gave the best results. We can see that the volume flow increased by 25% and the global homogeneity factor decreased by 8%, meaning that we have a better, more even cooling of the system. Yeah, that's it. I hope this proves that what Andreas talked about before is actually true. MODSIM is really helpful when designing and testing different alternatives. So it's really powerful, MODSIM. I definitely recommend you to try it if you haven't already. So thanks a lot.